All right, so chapter 12. Basically, chapter 12 is the concept itself is very simple. There are just basic requirements that you want. Chapter 12 is about equilibrium. What are the conditions or the requirements for an object to be equilibrium? And so the concept itself is very straightforward. It's very simple, and the equations involve just like two equations, but then you have to know how to utilize those equations. So, what is equilibrium? Equilibrium is something that like it's balanced. What does that mean? It's balanced. So what are the conditions? What are the requirements for an object to be equilibrium when there might be a lot of forces acting on the object, but the object still remain equilibrium, which means that it's not like falling down the cliffs or whatever. So what are the requirements in order for an object to be in equilibrium? And when we talk about equilibrium, there are two different equilibrium. One is static, which means that it's not moving, and the other one is dynamic equilibrium, which means that it is moving, but it still maintains its equilibrium state. Okay. So what are the requirements? And what we found is that the requirement would be that linear momentum has to be a constant, okay? And also the angular momentum has to be a constant. And you can see that I use the vector sign. It means that when you're dealing with more than just one dimensional, then all the linear momentum in all directions and angular momentum in all directions has to be a constant in order for the equilibrium in order for the object to be in equilibrium. Okay. So linear momentum has to be a constant, and angular momentum has to be a constant, and it is based on this requirement, we can actually see go a bit further. Linear momentum has to be a constant, and if you recall from Newton's second law, the net force acting on the object is basically equal to the time rate of change of linear momentum. So it's dp dt, okay? So this is from the Newton's second law. Net force acting on the object has to be the time rate of change of linear momentum. Now, if for an object to be equilibrium, it means that linear momentum has to be a constant. When you take the time derivative of a constant, that will give you, if that's a constant, that means that the net force acting on the object has to be equal to 0. Okay? So this is a requirement or the condition for the object to be equilibrium. It means that net force acting on the object has to be 0. Now, likewise, the angular form for Newton's second law is that net torque is equal to the time rate of change of angular momentum. Okay, so you have this. So if, again, this is a constant, it means that net torque has to be equal to 0 as well, about an axis or about a rotating point. So what are the conditions for the requirement? It means that net force acting on the object has to be equal to 0, and the net torque acting on the object has to be equal to 0 as well. Now, so I mentioned earlier that when an object is in equilibrium, they are static equilibrium, they are dynamic equilibrium. So if P and L they are equal to 0, it means that the object is not moving. So when it's not moving, it means that it is in static equilibrium. And if it has a non-zero value, but it's a constant, then we call that dynamic equilibrium. It means that it is moving, but then it's maintained its equilibrium state. And for those of you who are, in engineering, you're going to learn a lot of examples and take the course of statics and stuff in order to when the objects are in equilibrium and things like that. Okay, so these are just basically the basic concept from chapter 12. Chapter 12 also talk about all the things, but that's kind of beyond physics 311's level, which when you get to sophomore, you're going to learn that from other engineering courses. For example, the static, like elasticity and structures, all that stuff. So, but the important thing from chapter 12 is just this: how to apply this concept to analyze the situation when the object is in equilibrium. In other words, you want to find out what is the net force acting on an object. So you have to draw to analyze the forces acting on an object. Draw a free body diagram to find out how many forces acting on the object. And then you apply net force equals to 0, the equation, so that depending on the dimensions, if it's just one-dimensional, so you just have the net force in the horizontal direction that's equal to 0. If that's two-dimensional, then you have two equations. The net force in the horizontal has to be equal to 0. The net force in the vertical has to be equal to 0. If it's three-dimensional, then you have three equations. Okay, and so draw a free body diagram. Find out how many forces and set the equation according to Newton's law, that Newton's first law, the net force equals to 0. And then additionally, if you're asked to find the distance, whenever you're asked to find the distance, you have to use torque. Because if you remember, what is torque? Torque is R cross F. So you have to just sum all the R cross F terms about a chosen axis. So summation of R cross F, and then set it equals to 0. And so that's where the distance or the moment on comes in, because your R is distance, and force is just that. So whenever you do the problem, whenever you do the equilibrium problem, when the object is in static equilibrium, draw a free body diagram. Find out all the forces, and then set it equal to 0, and then set the torque, net torque equals to 0. So it's a summation. So the summation of R cross F, that has to be equal to 0. So when you calculate torque, it's just about choose a point that you want to calculate torque about. You don't have to calculate for every So take for example, let's see, what example can I give? We're going to do a lot of problems, so to apply this concept. So take, for example, let's say this, and you have an object right here, there. So you will have to find out what are the forces acting on, let's say, on the of the system. So this object, let's say this being has its own weight, that's a mg, and this block has its own weight, little mg, and there's a tension. So you have to draw the tension, and this is your theta, and this is the hinge. So the hinge will provide an upward force and a rightward force. So that's a FH and FB. So you kind of have to realize how many forces acting horizontally and vertically, and sum all the forces in the horizontal direction to 0, and sum all the forces in the vertical direction to 0. And then if you're asked to find the distance, then you can just calculate. You can calculate net torque about a point. So there are several points that you can choose. You can choose this point, you can choose that point, or you can choose some other points. But suggestions would be that you choose a point when there are a lot of forces acting on it, because when there are a lot of forces acting on it, and when you choose that point as the rotation axis, then you don't have to consider torque, because there's no moment on. If there's no moment on, there's no torque. So you kind of leave this out of the equation, and just so you kind of eliminate these two forces. You don't have to even consider in your in these equations and stuff. And then the forces you will have to consider is this, and this is the moment on, this is the moment on, and this is the moment on. Okay, and then you have to use your right hand rule to determine the direction. So use the right hand rule. And so that's R cross F. Take for example, this is the tension. Okay, what is your R? If we calculate torque, so let's say the torque that is contributed by this tension. So you will have R cross F, right? So your R here, let's say this R is the total L, so total length of the bar, and then your F is T, and then sine of the angle between them. What is sine of angle between them? This is the direction of tension. This is the origin, so your R is pointing in that direction, so the angle between them is this, not your theta. So it's actually 180 minus theta. So that will be the torque produced by this arrangement. So you have your R is this, and then you have your T, and then you're going to use your right hand rule. Use R cross F. So you have point your finger in the direction of the first vector, which is this is your R here. Okay, point your finger in that direction, and then sweep your finger toward the second quantity, which is the tension, and your thumb gives you the directions of the torque. So you can see that this is a counterclockwise rotation, and your thumb pointing out of the whiteboard, which means that it produces a positive torque. So this torque is positive. So you just leave it at that. Okay. Now, what about torque produced by the block, that little mg here? Okay, so let's say it is still R cross F, and then your R here is this D, and then your F is your little mg, okay, and then I'm going to, I'm sorry, so you have your D times your mg, and what is the angle between them? If you look at this is the location where the force is applied, and this is the moment on, which is D, and you can see that the angle between them is 90, so it's sine of 90, okay? And then let's see, so you have your R cross F, and then so RF sine 90, that's your magnitude. What about direction? Again, this is your R, so your R is in this direction, so you have R cross F. So R cross F, your F now is pointing downward because of gravity. So R cross F, so your thumb indicates the directions of force, which is negative. And if it's negative, you have to put a negative sign in front of it to account for the fact that it is a negative torque. Now, what about this torque? So let's say the torque produced by this by the weight of the beam. So you will have, let's say if it's located at the central mass, which is the half and it's uniform beam, so that's just the half 1/2 L. So you have 0.5 L, that's the moment on, and then times mg, which is the weight, and then sine of, again, this is the moment on. They are 90 degrees, in this direction. And then what about the direction torque? R cross F. R cross F. So you can see that again it is negative. So you can see that your net torque based on this diagram, your net torque would just be the torque produced by tension, the torque produced by the block of the mass of the block, and also the weight of the beam. Okay. So you add those three together. This is positive. This is negative. This is negative, and set it equal to 0, and then from there you can calculate, that D. Okay, so that's why you see that whenever you ask to find the location, you'll have to use net torque because torque involves the distance. Okay, so that's that. As far as chapter 12 is concerned, we focus only on static equilibrium, and in the problem set, in the recording for the problems, we're going to do a lot of problems, applying the concept. Okay.